Welcome to Chem 336. This is the very first video in the course, and we're going to begin with something very simple, yet has a lot of potential and a lot of role in general in organic chemistry, and that'll be aromaticity. Now, we've done some labs last year, if you remember, and a great deal of them smelled pretty good. And the reason was because of the presence of a particularly unique group called benzene, which we will talk about in just a little bit. But aromaticity itself it's a bunch of properties that governs how things go. But the aroma part itself has to be attributed to benzene ring, and we have a set of rules that govern on how things can be aromatic, right? So what is aromaticity? I've already explained that. It's a set of rules that make a particular molecule behave a certain way. And then one of obvious property is, one of the outcome of the property is it leads to a pleasant smell, which is where the aroma comes in. But the aromaticity itself is a set of properties that makes a molecule unique in a certain way. Okay, and if you remember from Chem 330, we talked about sp3 hybridization being tetrahedral, that is all single bonds, all single bonds. And sp2 hybridization is all double bonds, okay, which leads to a trigonal planar, and sp hybridization is triple bond. Okay, so it's supposed to be a single bond. My pen just overworked twice. It's just a single bond. sp2 means double, and sp3 means triple. While sp hybridization has no role in aromaticity, I just have it there just for comparison. All right, now how do we say I give you a molecule, or those properties I mentioned? Those properties, you can call them rules. And using those rules, we can determine whether the molecule has met the idea of aromaticity, or is it aromatic in general. And those are the rules. Okay, does the molecule itself contains a cyclic ring structure? What is cyclic? Means it just loops back, or you can just say ring. Okay, does the molecule first contains a ring structure? Yes or no? If the answer is no, then automatically the molecule can never be aromatic. All right. Second is, does the molecule actually, rules B and C are in a way interrelated? That is, they go together. Well, you can even think of B and C as a single rule. That's basically, you have to have alternate. sp2 is, you must have a double bond in the molecule, but then there should also be single bond, which leads to an important concept called resonance. For example, I mentioned to you about benzene. Okay, a great deal of compounds, whether natural or artificial, have benzene is a ring structure. Okay, now if you see benzene, it's got 6 carbons in a cyclic ring structure, and there's a double bond here, there's a double bond here, and a double bond here, right? These 2 carbons are sp2, right? Because carbons containing double bond are sp2, right? And then you have, again, sp2, right? Again, this is sp2, sp2, and sp2. Basically, if you notice, there's 2 carbons containing a single bond, double bond, and then a single bond. So you have a double, single, double, single, right? Double and single, right? One. Basically, I think I just drew the structure more inadequately, but you see that you have 3 double bonds and 3 single bonds, right? So when you have alternate double, single, double, single, double, single, that means, in other words, if you draw the molecule and you have a bunch of just sp2s, that should indirectly tell you that you have a double and a single, double and a single. Okay, so that's a giveaway that that the molecule could potentially be aromatic. But we're not still done yet. We still have one more rule. You count all of the electrons that make up the double bond. That is, we have 3 double bonds. So each double bond has 2 electrons, right? So double bond is 2 electrons. So you have total of 6 electrons here, right? So you have to use the formula of 4n plus 2. That is, you can substitute, you should be able to get 6 out of this formula. If you cannot get 6 out of this formula, that means even if the other rules are met, the molecule is not aromatic. For instance, I could substitute a value of 1 for n. I will give you this to you on the back of the test for appendix. You do not have to memorize this. So 4 times 1 plus 2 equals 6. So I'm able to get the 6 back out of the formula. So if all of these rules are met, then the molecule is aromatic. That is, it must have a cyclic ring structure. It must contain double bonds. That's because the molecule is planar. You see the way I wrote it here, I have double bond, single bond, double bond, single bond. That means I have just only sp2 hybridization in the entire molecule. But then also I have to have alternate single and double, right? Now, what I meant by resonance also is, let's draw the molecule. If we move this, we can move this double bond here. This double bond can come over here. This can come over here. That means a new molecule would have look like this. It still has a double, single, double, single. It's still all sp2. But the molecule now has double bond moved to a different position, right? That's because they're alternate. Only then you'd be able to move the bonds around. And this phenomenon is called resonance. That is, you can start with this or this. Neither of the structure is 100% always in this form. It can be 50% here or 50% here, but the ability to move the bond to an adjacent carbon and create a different structure within the same molecule is called resonance. Okay, so applying all 4 of these rules, and if you satisfy all 4 rules, then you can say your molecule is aromatic. All right, I got a bunch of molecules here, so let's apply the rules. Is my molecule has a cyclic ring structure? Yes, so cyclic ring, check. Does my molecule has sp2 double bonds? Yes, it's got sp2 between these two, and then there's a double, single, double, and then single, and then sp2 is only for the carbon containing the double bonds, right? Right, so that's met. So the double bond sp2 is met, and the double single is also met, right? And then I have 8 total electrons, right? 2 here, 2, 2, 2, 8. Now I will never be able to get 4n plus 2 equals 8. No matter what I substitute 1, I get 6. If I substitute 2, I get 8. So this rule fails, so it's not aromatic. So it's anti-aromatic. Okay, next one. Now, again, we'll start with the cyclic ring structure. Yes, that's there. There's a sp2, yeah, but it falls apart right away. There's a double, there's a single. There should have been a double here, but it's all single, right? It's all sp3. See, you don't have any more. You should have a complete sp2 surrounding, so that automatically fails. So we can straight away say sp2 is failed, so it's anti-aromatic. You do not even have to proceed further. Number 3. Again, let's start with the cyclic ring structure. Yes, it does. And then, does it have sp2? Yeah, sp2. It's a sp2, 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 and sp2. You see the entire molecule is covered in sp2, so that's good. There's double, single, double, single, double everywhere. I don't want to go through and do this, so the double, single works out. And then we have 2, 2, 2, 2, so it's 10. Can we get 4n plus 2 equals 10? You betcha. It's n equal 2 will give you 10. So that also, Huckel's rule also works. So that means it's aromatic. So these two are anti-aromatic, means it's not possible. Well, straight away we can say the molecule does not contain a cyclic ring structure, so it's anti-aromatic. Again, this is very important. I'm making 2 videos just to keep the time. Now, does the molecule have a cyclic ring structure? You bet it does. And then it contains double bond, sp2, 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 and sp2, right? You cannot say sp2 here because this is not a carbon. So this is where that little exception comes in. But so far, we have a sp2. So we're good. Anywhere we had carbon, we had sp2. We cannot apply sp2 to nitrogen because sp2 is only dedicated to carbon. So we're good. The only element left out is nitrogen. As long as we have carbons accounted for sp2, we're good. Now, is there a double, single? Well, think of this lone pair. If the lone pair is inside the ring, think of it as another bond, okay? This is equal to a bond, like a double bond. So it's double, single, double, single, double. So that works, right? The double, single works, right? And we have a total of 6 electrons, right? 2, 2. The lone pair has to be inside. I will show another structure where it will be outside. So it's 6 electrons. 4n plus 2 equals 6. N equals 1 will satisfy that. So Huckel's rule is satisfied. It's aromatic. Again, same thing. Does the molecule contains at least one cyclic ring structure? You think it does. Now, we're only worried about the sp2 for the ring structure, not for everything else. So if I just go around for the sp2, the molecule is, we're not too much worried about these. We can, but we're only interested in the aromatic property of the ring. So sp2 is met. We have 6 total electrons. Oh, sorry, I have skipped one step. We have sp2 everywhere, and then double, single, double, single, double, single. So that's worked as well. And we have 6 inside the ring. So 4n plus 2 equals 6, right? This is 2, 2, 2, 6. N equals 1 will satisfy that rule. So Huckel rule is satisfied. So this is aromatic as well. All right, this is very simple. All you're doing is applying a bunch of rules. And I'm going to make one more video where I show you a molecule with positive and negative sign. All right, so stay tuned.